Okay. So today we're going to look at reinforcement learning. And so last time I said there was this new additional thing that we added in terms of just in addition to just learning, right? So last time the learning part would be just estimate the mean rewards of each arm, for example. And if you just wanted to learn it, you would pull each arm like a constant number of times. So if you had 100 rounds and you had 5 arms, you would pull the first one 20 times, pull as in play the first option 20 times, or display the first option 20 times, play the second option 20 times, and so on. And you'll get an empirical average of how good that performance is, how good the performance of that option is. Okay, so that would be without this additional notion of decision making, as in being so this additional notion of earning, as in not being too regretful. So last lecture the whole emphasis was on trying to balance both learning and not being too bad in terms of regret. Okay, and we defined regret as what did you do in those 100 rounds versus what would have been the best option that you would have done if you had all the data beforehand, as in all the information about the mean rewards of each arm beforehand. Okay, because mean rewards are the only ones which count, because our objective was in expectation. Okay, even though there was a distribution of rewards for each arm, we don't care about the distribution because the mean is what enough. Anyway, so today's goal. Today's goal. These are the 4 goals. We want to understand what is reinforcement learning. Okay. Uh, there's going to be a similar exploration exploitation trade-off that we did that we kind of saw last time. Okay, so last time the exploration exploitation trade-off was, oh, there's this promising arm, should I play that one, arm as an option, should I play that one, or should I explore and get some more data about something which doesn't seem to be promising at this point. Okay, so that's a trade-off. So we'll make a similar trade-off today as well. And the kind of underlying object is called a object, as in like some mathematical description, just like it kind of makes it easy to understand what are the moving parts in this framework, is the notion of a Markov decision process. So the way we're going to build it is to start with a simple idea which is called a Markov chain. There is a lot of theory around it, but for us it's going to be a simple Markov chain from which we're going to graduate to what is called a Markov reward process, and then we're going to go to a Markov decision process. Okay, so that's how we're going to build on Markov chain. Some of you have seen it before. For example, Gibbs sampling was supposed to be a Markov chain, when doing those, when getting your samples. The third object that we want to kind of familiarize ourselves by the end of the day is the notion of a policy and the notion of values. Okay, so policy is nothing but what do I do in every state or every context, basically. So that's a function. Okay, just think of it as something which maps inputs to outputs. In this case, the inputs are going to be state or context, and the outputs are going to be some action. Okay, instead of labels, generalizing labels basically. And values are going to be some notion of like a score that you can say, oh, this is a valuable state to be in, or oh, in this state taking this action is valuable, so something like that. Okay, and so it's again a function, so it maps a state to a number, or a state and action to a number. Okay, and we'll see this quite a bit, but I'm just doing a teaser. The last thing is going to be the notion of Bellman equation. Okay, so what are these objects? They seem strange. Bellman equation, expectation equation, and optimality equation are some sort of recursive definitions of recursive equations which kind of relate a value at a given state with value at some other states. Okay, basically, or and so what's the use of such an equation? Is such a equation is kind of used to derive some very good, I guess at least the baseline techniques in reinforcement learning. Okay, which is the original problem. And one of the popular techniques that we'll kind of touch upon today is called Q learning. Okay, so Q learning is a really old algorithm which kind of works really well, and in fact, maybe now we'll see some of its, not Q learning itself, but that type of reinforcement learning algorithm. How do they perform? So here are some motivational videos. So this is one of the games from Atari. Last time I showed you a screenshot of all the 50 games. Some of you probably have already seen this on media, but this is a game called Breakout. Okay, I don't know how many of you played this game, Breakout. A couple of you. Okay, so basically, for those of you not seen this, you basically have to balance this ball. It should not fall off from the brick, from the support below, and you have to kind of keep clearing the bricks at the top. Okay, and Okay, so in this case, the yeah. So this is just a video trying to show that So the actions are your actions are move left, move right, basically, or to what how much amount and so on, and your input is actually the screenshot. So screenshot at every some frames per second. In this case, the algorithm has figured out what's the best thing to do. Okay, um, which is to somehow send the brick onto the side so that it can clear out all the bricks at the top. So send the ball above. So that's the game of breakout. So the agent playing there was not human. Okay, we can also of course play it, and in this case it was the computer which figured out by trial and error. So reinforcement learning is a trial and error method. Okay, so in every situation you kind of try a few things, see which one's more promising, which one's less promising, and double down on that. Okay, and similarly, it's the same thing that we saw last time. We had to do trial and error because we had no information about the performance of each of our option. We tried some others, got an estimate of how good they are. Maybe some were really promising, so we doubled down on that. Okay, so that was the exploration exploitation diagram. Here's more recent game, still a couple of decades old, I think. How many of you remember this type of a game? What? Doom. So here again, it's a computer agent. I mean, I don't know if it's the actual map or not, but so again, the agent is trying to figure out like its input is going to be these frames. Okay, what it's seeing, what humans are seeing, is what it is also seeing. Okay? And next third motivation is a small game. How many have played this one? At least once are aware of this one. So this is a game where you're supposed to, I guess, push this bird up and down, doesn't hit the pipes. Uh, and so this again is being played by an agent. Actually, agent for us just means a software. In this case, it's been trained. This is actually being trained using Q learning or a variation of Q learning. And so we'll see today what the basics of Q learning are. But to get there, I mean, you can always directly jump to Q learning, but to get there in a very nice way, so you understand the basic building blocks, is what the rest of the lecture is going to be about. Okay, and yeah, so I think so. So we're going to start. So I'm not going to spend too much time on decision making because last time I spent a bit of time. But what is the? I mean, the end goal is so many for many. I guess applications. The end goal is not really to just predict really well, right? Once you predict really well, you're going to take some decisions, and that's kind of uh, uh, ubiquitous across many different areas. So here I'm talking mostly about areas as different as like economics and operations research, focusing on policy strategies and so on, all the way to machine learning and AI. Those also have to kind of feed into some decisions like maybe picking stocks or approving a loan or something like that, or finding fraud, and all the way to psychology. So there are some relations to all this to a central object that we'll study today, which is reinforcement. And here I've just listed a few applications like really physical applications like flying a drone. So of course manually you can do things. You can buy a DJI or one of these things, or in operations, for example, you may be solving some complicated decision making problem of forecasting inventory and then figuring out how much inventory to stock, subject to constraints about how much money you have, how much shelf space you have, or warehouse space you have, and so on. So all these problems have something which is forecasted, something which is the state of the world, how will the state of the world look like in the future, and some things which are going to be decisions. And these decisions need not be singleton decisions. They could be correlated. There's some constraints like cost constraints, budget constraints, or capacity constraints, things like that. Same thing with logistics, and games are a little bit different, but we'll also see what uh, they're also essentially you need to forecast how well this move is going to be. Hopefully, this move is going to have an influence on you winning the game at the end of the day. So there's some forecasting and some decision making here. Okay, and here are some pictures of the same thing. Um, those who have worked in the industry, you can abstract out, the stylized problems there as some combination of forecasting and decision making. Um, and this is what I had shown last time, that RL is part of the top 10 list, breakthrough technologies from a couple of years ago. But that's not, actually, let me show you another thing. Uh, let's go to our forum. I forget the link. That's why. So, so this is from actually today, I think. So which is Alpha Star. So some of you might have heard of AlphaGo, and I think I referred to AlphaGo as well, which is from 2016 actually, and there's been several iterations of that recently. And this is uh, it is from yesterday, a blog post from a company which is whose agent, game playing agent, Alpha Star, is at the grandmaster level in a game called StarCraft 2. So how many of you have played RTS games? Okay. How many of you have never heard of RTS before? Okay, real-time strategy games. Okay, so here it's basically you've been given a map. You kind of it's like Age of Empires or many of these games. Okay, so StarCraft is something that you can actually, I think some level of it is free to install on Mac and Windows, so you can try it. Um, and so they use a variation. So they don't just use reinforcement learning. In this case, they use multi-agent reinforcement learning, which has its own, what is the change there? We're not going to discuss in this class, but they claim that they have reached this level of performance. Actually, in fact, they have a some sort of um, performance curve where eventually they've reached somewhere over here. So you can read this blog post. It's on the forum. Uh, so they claim they reached the grandmaster level. Okay, so which is like really good compared to an average amateur player. So let's come back here. And this is what we saw. And this is the AlphaGo from 3 years ago. And now there's several versions, new versions, and we're going to discuss a little bit of. Actually, we're going to discuss the details of this particular system, this particular agent next lecture as a case study. Okay, so today's lecture is not going to be related to deep learning, just same as last lecture where we did not really discuss deep learning. Next lecture we're going to bring back deep learning plus reinforcement learning in the picture. So today is mostly the basic building blocks for an agent. What does the simplest agent look like? It's going to deal with policies, it's going to deal with values, and that's what we're going to learn today. Okay, videos we just saw. So what's the need for reinforcement learning in the sequence of things that we've seen? Last time we saw two things: multi-arm bandits and contextual bandits. Okay, where multi-arm bandits we just had actions, so no states. So every time a user came, we didn't care about their profile, basically their context. We just said, oh, is website one better, website 2 better, website 3 better. Okay, so those were the three actions. Our action was to show either one of these websites, and for each website that we show, we had the reward, which is like whether they click on it or whether they make the purchase or not, right? And by exploring, by trying out different websites and being sample efficient there, while not being too bad in terms of earning money at the same time, we figured out how to trade those two off using several techniques. Okay, epsilon greedy, UCB1 or thousand sampling, EXP3. So those are all different methods, but they have the same idea. How to kind of balance, randomly try out something else when you know what the most promising thing is. Okay, don't always go for the most promising thing. Was the kind of key idea. Next, contextual bandits. There's this notion of a state. So users come with their profile, and this is actually more closer to the application that we saw last time, which was the I think it was MSN.com maybe, where users have a profile, demographics, and how much time did they spend previously, what do they like, and so on, what do they like, and so on. And then your action was to show a list of articles or place the articles which you think are most useful for this guy or this user, and uh, and 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 the reward is a function of both what you did and what is the user. Okay, so there's 2 hours going into the reward that you could get. Okay, and here again you want to figure out in every state or every user type what's the best action, what's the best rank list of articles to show. Okay, so there's a function here just like a classifier function. There's some input, there's some output. In classification, the input is a feature vector, the output is a label. Here the function here is the input is a state, so this is still a feature vector. Output is an action. Okay, it's a generalization of a notion of a label. Okay, so this is the function. This function is called a policy, and we're going to revisit it again. Okay, and the only difference from these two, so there's some additional arrow here and this guy. Now the difference is going to be that the action is also going to influence what's the next state that's going to come. Okay, so this is the one additional arrow that came up, and also there's this dash arrow, which just means that the reward may not be immediate. Okay, so if you take some action today, like let's say today you uh, you know, let's say 10 days ago you kind of bought Tesla stock. Okay, then the result of that, like a huge increase which happened after, I guess, the earnings report yesterday or something, is not immediate, right? So you did something long time ago, and now you have a you observe a reward. Okay, so that could also happen over several time steps. Okay? So anyway, we cannot revisit this. The only difference between this and this is there is a feedback loop. Okay, so your actions influence where you end up next. Okay, whatever user. So if you really kind of show bad recommendations, then the user who comes back is going to be not in a happy situation. Like they may not be really anyway. They may have a memory of what you did last time, and so they may not be. Uh, they may not stick on your platform. So with that, if are there any questions about the lay of the land? So far I've been just being quite hand wavy. So we're gonna get into some details soon. Okay. So so the first slide is just an overview in the sense of the items highlighted in red are the items that we're gonna spend some time on. So RL, or reinforcement learning, is a way to address the problem of sequential decision making. So what is sequential decision making? Involves some forecasting component and decision making component. And sequential aspect just means that this thing runs in a for loop. So you keep forecasting, keep making decisions. Those decisions have some rewards that you also observe, and then hopefully you can improve your forecaster, and therefore you can improve your decisions and so on. So that's what we did even in the online learning case in the previous lecture. We were taking some decisions, taking some actions, showing some website. We got some rewards. That reward helped us better estimate our model. In this case, the forecasting model is simply what is the mean reward for each arm, and then therefore we could take better decisions. Okay, so that's the sequential decision making process. And the ingredients in RL are basically there's going to be an environment. That's the first guy. There's going to be an agent. That's us, as in the software. And the key thing, which is new here, is that our actions that we take have influences on what's going to happen in the future, in the sense of the state of the environment in the future. Okay, and the agent can get a feedback signal just like before rewards, but they need not be immediate. Okay, so there could be delay. And what we want to do is to select actions to maximize the total reward. Okay, so total reward just means I'm gonna kind of I'll have a lifetime or some horizon. Okay, maybe I'm gonna keep doing something forever, or I have a horizon. Maybe I have a campaign, I'm gonna do it for a year. So over that horizon, how much reward I collect. Okay, so that's the by taking different actions like showing ads, different types of ads, and so on, right? So RL provides sound answers to this question of how do I select actions to maximize total reward over a horizon, for example. Okay. So let's tease apart each guy. So first we look at environment, then we look at agent, then we look at reward and so on. Okay. So first, what's the environment? So the environment is an object which looks at agent's action. I'm going to index it as capital A subscript T. Capital A because it's going to be a random variable for us eventually, but it could also need not be a random variable. But for simplicity, we're going to use A subscript T to say what's the action that was taken at time T. And because of that action, as I said, actions have consequences today. Last time, actions did not have consequences. Last lecture, the consequence is going to be a new state, a new context of the world, which is st plus 1. So today's action has a consequence on who's going to come tomorrow, okay, or what's the situation of the world tomorrow, and that's st plus 1. And I'll also generate a reward, rt plus 1. Okay, so that's not tomorrow's reward, it's a consequence of today's action. Okay, so just a time index difference, but that's notational. Okay, so current observation based on which I'm making this action is st. Okay, so at st I make an action at, I get to next state st plus 1, and a reward rt plus 1. Okay, those are the four key things. And although it's not very central in general, but we'll see that we can make this assumption for, I guess, ease of discussion here. We don't have to have this assumption while designing RL framework or an algorithm in this space. But the assumption is a Markovian assumption. Okay, what does Markov assumption just mean? Markov assumption is just a memoryless assumption. It's just saying that I took an action. I went from some state to some other state. That state transition. Okay, so I went from a state st to a next state st plus one. That does not depend on what were the previous few states. Okay, so maybe so generally, like, think of these capital letters as random variables. So there's the states being changed over time. Typically all the states from before could influence where do you end up next. Okay, there's no reason a priori to say. So basically, the assumption is that this condition probability is equal to this probability, which means that you can drop these random variables. As if given this random variable st, the previous random variables have no influence on the probability of being in any new state. Okay, so that's like a given present. The past has nothing to do with the future. That's like a very informal statement. So that's what Markovian assumption means here. And we'll also kind of assume for our discussion that everything relevant is observed. There is situations where you may not even measure things. Like you cannot measure the how happy the user is. Okay, you can only see what the user does with your platform, right? I mean, so that's partial information, partial observation. But for us, we'll just assume we observe everything about the state of the environment. Okay, environment. So what's an example of an environment? It's a user. Okay, it's like a user who keeps interacting with your um, website, for example, or it could be the game engine. Okay, game engine with whom you're interacting with. Like you're moving the joystick, you're changing the control. The game engine is responding with going to the next state, right? So, for example, in the breakout game, you move the paddle to the left and it bounced the ball back up. So the next states are going to be, the ball going up and clearing some of the bricks, right? So that's an example of an environment. Okay. Any questions about environment? Yeah. So I take an action, the environment will spits out a number, I mean, a reward number or score. For example, in the games case, it's easy. You can just see a score which increments. Reward could be just a click. So I took an action. I showed a particular website. Like remember last time also we had a reward, right? I show a particular website. Then there's a certain click-through probability or certain sale probability. So that's with some probability they'll click, and hopefully that's higher for a good website design maybe. So that's the reward. Yeah.
I think I'm just missing something for the Markov assumption of the future is independent of the past and the present.
Yeah.
It looks like at least the probabilities are right. It looks like it's conditioned on all the past states.
Yeah, we are saying that condition on all the past states, the probability of being in the next state is as good as saying condition on just the current state being conditioned on the current state only. So I should have written it the opposite, I guess. The right hand side is equal to left hand side. It's just saying that I can drop these bits. This probability is the same as this probability. So
So it's that you drop.
yeah, maybe I should have flipped the equation. So initially, I mean, a priori you would say, oh, whatever happened before could influence what's a randomness, what's a new random variable today. First of all, note that we're not in the IID world. I mean, what happened previously has influence on what's going to happen in the future. Okay, if it was IID, then it wouldn't matter. When this would be dropped, and it's just a probability of ST plus one. Okay, so that's the non-triviality here, that data that you're collecting to learn is actually influenced by what did you yourself do in the past. Okay, so the data is not IID, and so all the nice things that you did, like you can permute observations, split into test and train, and all that stuff, that doesn't happen here. Okay, you can't do that. Like here we are trying to find a policy, right? It's a mapping from state to action. But to find a policy, you could think of it as a classification problem, except that there's dependence across time, okay, of observations. So next, the agent. As I said, the agent observes. I mean, at a given current state st, they took an action at, and they observe rt plus one and st plus one. Okay, so that's what they do, and so agent's objective is to maximize this quantity. Okay, which is so what is this quantity? Is the expected total future reward. Okay, so it looks what I'm trying to write here is, okay, you're at time t. Okay, at any given time t, you want to maximize the expected total reward. And so the total reward, let's assume infinite horizon, just means that as if I'm gonna keep continue on playing on over and over and over again. So I have an infinite lifetime. So reward that I can get with the current action that I take, reward, and eventually I'll get somewhere, some other state, the action that I can take there, and then action I can take there, action I can take there, in expectation, they're average, but with some discount factor. Okay, it's like the time value of money type of a thing here. So it's a discount. So I kind of discount the reward, that expected reward I can get in the future, by a little bit. Okay, so think of gamma as 0.9 there. So it's just the average of all the rewards I can get, and here it seems like, oh, what is it that I'm even changing? Here I'm actually controlling agent's objective is to maximize this number, but for every number that I can get, it depends on which states I bump into, right? If I take an action 80, I'll get to some ST plus one, and there will only be some actions that I can take, and depending on those actions, I can only collect some rewards, and because of that action, I would get to some other state, and so on. And so agents control is of course the actions that it can take in every round, every time instant, while maximizing this quantity. Okay.
Is gamma applied to everything except for the first value? Or
I should have written it. So r t plus 1 plus gamma r t plus 2 plus gamma square r t plus 3.
And gamma is less than 1.
Yeah, gamma is a number between 0 and 1. Yeah.
The way to understand it is taking a current action now will influence the end action very little, the end reward very little, right? Which is why you're writing gamma square.
No, it could. So gamma is something I choose as a designer. The current action could have really long-term consequences, like the butterfly effect, for example. But I may discount the reward that I'm getting. So when I care about the current actions, like, is this action good to take now? I don't really care about the rewards I'm getting 100 days later, for example. That's my choice. Maybe I care about it, then I'll have to change gamma. Maybe I have to set it 1. Okay. And as I said, the central theme from last lecture is that now my action is going to influence the website I show. Influences who else comes to my website tomorrow, for example. Okay. And so the key trade-off, in addition to this, I guess the key trade-off is that I could trade off the current reward. Maybe I would prefer getting a less reward with the hopes that I'll be in a better state tomorrow and make more rewards. For example, I could give lots of coupons today so that this user is like, it becomes more and more loyal to my product offerings, and so I can maybe charge a premium later once they are loyal. I guess it's a bad thing, but that's an example. Okay. Yeah.
So the current action that I'm taking is based on a reward. In the state
It could be based on whatever you did so far. So current action that you want to take is a mapping from current state and whatever you've learned so far. So
some previous reward is also an input, right? To take some decision.
yeah. So I, as an agent, I've been like, let's say, navigating through, one in this setting up to time t, I must have taken t minus 1 actions already. Okay. Those actions led to some rewards. Okay. And I saw some states. All that information I can use to decide what action to take now. But the environment itself, environment is in state st. I took an action 80. It'll only go to some next state st plus 1. It doesn't depend. That state transition doesn't depend on the history of states that the environment has kind of passed through. So that's the Markovian property of the environment. I, as a decision maker, I can look up what all I did and what flopped and what worked for whatever time I was in operation. Right? Yeah.
What makes the action? What makes to trigger that particular action?
Yeah.
Is a function of, let's say, I can take some whatever reward that I'm getting now
Yeah.
for that particular action.
Yeah.
My time is t, and I may get a reward of t minus 3. Or I'll get
Oh, okay. You're talking about delayed rewards
Yeah.
here. So yeah. So if I take an action today, let's say I showed website, the best, the like website 1, and I got some click throughs. Those click throughs could be result of previous campaigns, previous actions that I took about, like spending ad money on Facebook or whatever, Google AdSense or whatever, could have led to today's higher click rate as well, in addition to my action. So there is that long-term aspect of actions that you took in the past could be also be added together to you seeing a number like a conversion rate today. Okay. I'm talking in terms of website stuff, or just to keep the theme same.
Some other services that take account of like all the previous actions. For example, any game.
No, all algorithms, sensible algorithms, have to consider what all worked and what all did not work. So it's a trial and error situation, right? At the beginning, I don't know anything about the environment, how the environment switches between states, and what's the value. I mean, if I take this action, what rewards I'll get, I don't know. Just like in the bandit situation. In the bandit situation, I did not know what was the rewards I would get if I showed website A versus website B, right? Here also, I don't know.
Something like state action rewards, something.
Yeah. So given that trace, it's going to be very similar to a supervised learning problem. Given that trace, maybe you want to condense it into some policy that at the given state will tell you what's the best action to take. Okay. The only non-triviality is that trace or previous action state, reward, next state, whatever that information is, it's dependent across time. Okay. It's not independent. It's not IID that you can just run a classification technique. Okay, or something like supervised learning technique. Um, Okay, so the third part is reward, and reward is just a scalar signal, just a number, maybe a real number or a integer, and it just indicates how well the agent is doing at step T. Okay, so at step T, I took an action. Okay, actually, maybe I should call it T plus one. At step C, I took an action capital AT, and I got some reward RT plus one. Okay, so it's just an indicator of it's like an instantaneous reward. It may be really good, but it could be like if you're short-sighted, then that's good for you. But because maybe later on you went into bad states, and there whatever action you took, you couldn't generate much reward. Okay, that could also be possible. Okay. For example, you can steeply discount your prices today, and you get lots of sales. But then nobody comes back again, so you're it doesn't matter what you do. Okay.
Do you reward everything that's in the past we're added to, or are we looking at that discounted expectation?
This is the instantaneous one, but our objective is to collect maximum cumulative reward throughout. Like let's typically operation starts from t is equal to 1 to t is equal to infinity, or like some capital T, some number of rounds.
So it literally is just a summation of all the R's and
Yeah.
maximize based on.
Yeah. So you may ask, like, why can't I do this? Like, what's the complication here is that you don't know what rewards I get at different situations, and so you have to learn. So there's a learning problem here, just like in the bandit situation. In the bandit situation, if you knew the mean rewards of each of the arms, you would pull the best arm all the time. Okay, the best arm in expectation all the time, and it would have some randomness, but in expectation it would be the best. Here also the same thing. If you knew the state transition dynamics and the given every state in action what the reward number would be, you would figure out what's the best action to take throughout. Okay, that's an offline problem in the sense you don't even need to do a trial and error to figure it out. Okay, I mean you can do trial and error to figure it out, but I'm just saying that that's a different problem. Here we have to learn while doing well in terms of total reward. Okay. Yeah. Yeah. Yeah.
So I think over here also, because when you put that expected value of
Yeah.
reward, that was kind of a geometric progression equation which you can find out this sum.
Uh,
You can find out what will be the total reward over here.
we'll see that. We'll kind of spend some time on that. Yeah, I think you have the right idea, but let's kind of make it much more precise. Yeah, the sum is what we want to kind of maximize, but the controls are like you cannot figure out like 2 steps ahead what the control is, because I mean you can, but so there's some non-triviality here. Yeah.
Are we trying to do something kind of similar where we are trying to, in less number of steps, we are trying to maximize the reward where we finally end up?
No, we have been told, like in the game setting, you clear all the bricks in breakout, you win, right? We care about winning, but we have to take these intermediate actions that could have long-term consequences, like or multiple frames, for example. Uh,
There's a kind of trade-off situation. Like we have
there is an exploration trade-off. Like for example, you could do random things just to learn what's the best reward you can get at a given state, but then you may not be making progress. You may not be collecting, like you would have wasted those 50 rounds just trying out random things, whereas you could have made some progress in the game, for example. So there is a trade-off between learning and earning here as well, because if you have a finite horizon, um, I mean, if you have, yeah, if the game terminates after some time, okay. But we'll get there. Okay, so those details we'll get there. Yeah, I mean, this slide, I guess the takeaway is that there's a reward signal every round. It could be it could be zero as well, which means you're not seeing anything. I mean, you're not seeing any reward, let's say. Any positive feedback of what you did, for example. It could be negative, for example. Oh, it's a bad thing to do. You can get such information. And that's what it here. The reward hypothesis just means that everything, like if the agent needs to perform a goal, like clear a game, or like figure out like best selling strategy compared to hindsight, in let's say in inventory management or promotion planning type of problem, then everything can be encoded in terms of the reward signals. Okay, so as long as you can give the right reward signals, the agent can achieve that promotion planning goal or inventory management goal or clearing the game goal. Okay, so yeah, I mean, I think this slide is just a summary of those three things: environment, agent, and reward. Goal is to select actions to maximize this cumulative reward, or here I'm just saying total future reward. Total is the cumulative part. Actions have long-term consequences. Not always. Sometimes actions don't have. So actually, you can apply the algorithms that we see today to the things that we studied last lecture. Okay, so there is really no state. For example, multi-arm monitoring, there's no state, but you have to figure out what is the best actions. Okay, because you're collecting rewards. So same problem. You can apply the algorithms here. There. As I said, rewards may be delayed, and it may be better to sacrifice immediate reward to gain more long-term reward. Okay, so for example, you coming to study, you're undergoing an opportunity cost, right? You could have been in an industry making more money, but the whole point is you kind of get less reward now, but hopefully you have better reward later. Okay. So that's another example. Um, okay, so here's the interaction, block level interaction. Um, So agent observes a state and must have received a reward from the previous action that they took. So that's not very important. So they receive a state. Okay, they observe. Oh, I'm in the state. Okay, what is the best? What is the action that I need to take? Okay, it could be the best action, or it could be something to explore. For example, if I don't know much about the environment, and when they take this action, they get this two observations. Okay, they get to the next state, which they observe. Maybe the world changed like this, or the user changed like this, and they also get the instantaneous reward. Maybe they click through and bought the product, or maybe they did not. Okay, and now given the new state, that influences what action I'll take again. Okay, and again I'll get the next state and the subsequent state and the next subsequent reward. Okay, now these are the numbers I want to add up. Okay, so I want to take these actions which are dependent on current states to get to next states. Hopefully I get to better and better states where I get more and more rewards, for example. Okay, that sum is what I care about in expectation. So very quick slide on what's the difference between ML and RL. ML is in like basically supervised learning. So there is no explicit supervisor, as in like there is a reward signal, but it may not tell you whether the action that you took is correct or wrong. So, for example, in classification, if you say a class is cat when it's not a cat picture, then you get get a response saying it's not a cat. I mean, in fact get a response saying it's a dog. So you would actually get supervisory signal, very strong supervisory signal. But here we only get a reward. Okay, it could be 0 or 1, for example. And as I said, feedback is delayed. Time really matters. So in the sense of it's not IID data. So there's a dependence on the action that you took has influence on what happens tomorrow. Okay, what's the state which comes into tomorrow? Okay, so that's this too. And so you can, in terms of feedback level, you can say that the most informative feedback is supervised learning, and reinforcement learning has some supervisory signal. Okay, and unsupervised learning by definition, there's no signal. It's just basically the eye of the beholder. If they like the clusters, then it's good. If it makes sense with respect to domain knowledge, it's good. Okay. Yeah, I don't want to spend too much time on this, but it's basically supervised learning. There's inputs and outputs, and the signals is basically the input-output pairs in training, and you just want to find a mapping from inputs to outputs. Similarly, in reinforcement learning, you again want to find mapping from input to output. In fact, input is going to be the state, output is going to be the action. So generalization of feature vector and label. Okay, that's this part. But the actions are indirectly giving you the signal. Okay, so the actions are exposed to the environment gives you a reward signal, and the reward signal need not be actually the label of this label or the best action to be taken in the state. Okay, and in fact that also influences the next state, and so there's some additional feedback loops going on. That's what I've been kind of emphasizing for the past couple of slides. So So that was just motivation so far. That there's an agent, there's an action. So there's an agent, there's an environment, and there's a reward part. Now we're gonna fix some of the most basic building blocks that will let us talk about what is called a Markov decision process. Okay. So for the next 10 minutes or so, 10-15 minutes, we're gonna talk about three components. One is called a policy. The second thing is called a value function. The third thing is a model. Okay? And these are not new, extremely new things, but something to kind of fix our, I guess, terminology. Okay, how we speak about this. So, what is a policy? A policy is just an agent's behavior function. It just means that it's a mapping from state to action. Okay, that's it. It's a function which, given a state, tells you what action to take. Okay, that's a policy. A value function is ascribes a value to every state or every state action pair. Okay, so it's again a function. So any given state, apply the function, you'll get a number. How good the state is. Okay, maybe you're in some state which is really good, maybe in some state which is really bad. Okay, it's a number for that state, or it could be a number for both a state. If in this state I take certain action, this is the value of that state action. Okay, in that state taking that action. Okay. And model is just our representation of how the environment behaves. A model is actually the model which is a transition from, okay, if I'm in the state, if I take this action, this is the probability with I'll go to the next state. Okay, so that's a model of the environment. It's called the transition dynamics of the environment. And we can also have a model of how the rewards also come. So for example, in this state, if I take this action, I'll get this type of a reward. Okay, there could be a function like that. So that's a model. So I'll describe that in detail. So as I said, it's a function. So a policy is a function which goes from state to an action. And in general, the two types of policies. One is a deterministic policy, where the agent is saying, "Oh, I'm in the state. In this screenshot of the game, do exactly this." Okay, that says, "Oh, if in this screenshot, do exactly something. Go left." Okay. Whereas there are some stochastic policies which say, "Oh, you're in the state. Flip a coin and do something." Okay. Maybe there are three options: flip a three-sided coin and do one of these things. Okay. So that's a randomized policy. Okay. But ultimately, we're going to represent a policy or a function like this as pi, just like a supervised learning function f. Except you want to learn this pi so that you can keep at every new state you can kind of apply pi, and hopefully you can take those good actions so that you can collect this long-term reward. Okay. So here's an example. So what is the environment here? It's this maze, and you start from here, and your goal is to go there. And I've also written rewards, but let's not focus on the rewards. This is what I want to focus on: actions, north, east, south, west, and states are going to be the 2D locations. The like maybe this location is some number like 3x1 or something, or 1x3 or something. So here's a policy, graphical representation of policy. What is it saying? In a state, maybe this white block, go north. Right? Simple example. And so this is a policy completely. It tells you at every state what should I do. This is a deterministic policy. Okay. It's just saying, oh, if you're in this policy, sorry, if in this state, go this way. If you're in this state, go that way. So you can evaluate how good the policy is in terms of the total reward collection, and we'll do that soon. Any questions about a policy example? This is a visual policy example, but for simple, in general, this is just a mapping from state to action. Okay. Next is the value function, and so this is the thing that we've probably not seen before, and so let's spend a minute or two here. Value function is as I said, a score that you assign to a state. Okay. Or you could also assign it to a state and action. We'll see that a little bit later. So here, what is that function trying to do? That function is trying to do is trying to say, oh, you're in this state, and let's say you have already decided. Somebody told you what policy to apply. Okay, in the sense that maybe some expert or maybe the software told you what policy to kind of keep applying in different states. Okay, then it's just saying it's basically a prediction of future rewards, okay, from that state onwards. So that's a value function. It's used to evaluate the goodness or how good the state is. Basically saying, oh, in this state, because this was the state, I know pi of s, I know what action to take. Maybe I'll get a reward this, maybe I'll go to some other state, I also know again pi will tell me in that state what action to take. Maybe I'll get this reward. It's random, right? All these rewards are random. Again from that state I'll apply pi of that state, and then I'll get to some other state. I'll get this reward and so on. So, but I have to start from this state. Okay, this condition on st being this little state, starting state s. Okay, and the expectation of this over pi. Okay, over pi could be random, like the policy could be random, right? Or I mean, there's also expectation even without pi because the next state could be random. Okay, so from st I could go to st plus one, which could be arbitrary, right? So it need not be deterministic. So that's the expectation for that. So we've seen this before. Okay, this type of summation before, which was in fact the goal of the RL agent. And here we have just encoded that as, oh, if you already decided a pi at this, then the value of a state given the pi is just this sum. Okay.
Means
Yeah.
we are just encoding the state. That's it.
What is it?
Value function is we are encoding a particular state given the policy.
Yeah, given a state, it will return a number. So think of that as a function. Okay. Okay, function which is kind of related to the policy, a policy. Okay, every policy there's going to be a function like this. Okay, for different policies, if there are only 10 policies in my world, then there will be 10 such functions. Okay, 10 such API calls. Every time I pass them a state, it will give me a number of how good that state is under that given that policy. Okay, it's just a mapping from a state to a number.
Let's say in a game I've taken 3 steps in my course and the first is, let's say my game ended in only like 3 steps.
Yeah, then there will only be 3 things, right? This is not middle.
So I just take the submission of these
Yeah,
kind of product, right?
yeah. So yeah, this is the only thing is scaling geometrically. Yes. So anyway, let's look at an example actually. So did I put something? Oh, okay. So here is an example of a value function. Okay. So again, this is the picture of the 2D maze. As I said, each white block is a state. I mean, black box. I mean, the black part you can't even enter, so it's kind of unreachable. In each block, I'm putting a number. That's the value of that state. Okay. So being here is the most valuable in this picture. Okay, because you are right next to the goal. It's -1. You can just think of it as 0, for example. So why is it -1? Is because there is a reward of -1 per time step. So you being like one step away from goal, here, means that you are, let's say the policy is that policy that we saw, like going this way, going this way, going this way, Okay, then we know that here the policy is deterministic; it will always go this way, and so the value is going to be the one negative reward that you will collect because you are one step away. Yeah.
This would be an example of obviously a learned value function already. It would just start with all of these random or something.
Yeah, good question. So learning, we have kind of paused learning for a moment. We just want to understand what a policy was. Ideally, we want to learn a policy, and if we learn a policy, we'll kind of know what the value function is. Okay. Or so there are a couple of learning things that we want to do. We want to learn the best policy so we can collect the total reward, or an equivalent object is to learn good value functions so that we can collect total reward, so that we can make good decisions. So always we want to figure out what the good decisions are. If somebody tells us a policy, then that's going to tell us what decisions are. If somebody can give us value functions, we will be able to reverse engineer a good decision pretty soon. Okay, that's why we are reading out values right now. Okay, but the goal is always to make good decisions to kind of maximize the total reward. But for the previous slide and this slide, I'm just trying to show you an example policy and an example value function. Okay. So here the value function is basically saying, oh, every time you are away from the goal, basically I increment by -1. So basically this state is most valuable. This state is most valuable. For example, here, right, it's -21. This state is less valuable than this guy, but this state is also less valuable than this guy, and these states are even less valuable than this guy. So it's like how good. So if you somehow magically end up in this state, happens to be -24, you're kind of doing bad. Okay? If you somehow magically end up maybe -22, you're slightly better. Things like that. So, but anyway, once we figure out what a value function is, we're going to figure out how to make good decisions if we can learn such value functions. Okay? So learning, I'll kind of comment pretty soon. And the last part is a model. So what is a model? Is it could be the true way in which the environment itself behaves, or it could be something which predicts what the environment will do next. Okay, by which I mean that so there's going to be two objects, script p and script r. Okay, so what is script p saying? Oh, you are in state st, which is maybe little s. Oh, you're going to take action which is going to be little a. Okay, what's the probability with which you will reach the state st plus 1, which is little s prime? Okay, so that's a model. It's just a transition probability number. Right? Transition. This is just a conditional probability saying, oh, if you're in this state and you're taking this action, what's the probability that I'll get to this state? Okay. So that's it. That's this. This is a model if you have already access to such a number. Okay. And reward at a given state and a given state and a given action is the expectation of, as I said, this is a random number. So the average value given the state and action could be model as well. Could be the model description. Okay. So any questions about model notation?
PV.
This is just a short form for this. This is a probability. Probability of going to next state given current state and action.
Oh, okay. I'm just saying it's like a regular PV.
Yeah, we just use a simple notation. I mean, a script notation here.
Okay.
But just instead of writing this whole thing, it's just saying probability of being in state S, taking action A, going to state S prime. So time I'm not showing here, but
S prime would mean the next day.
yeah. I mean, next state is a random variable, right? Given in this state, so I'm going to give some examples and it will become clearer. In a given state, you take an action. It may not be deterministically. You may not deterministically go to another state. Okay. You may, with some randomness, go to some other state. So it's just saying, oh, in this state, you take this action, this state, and this action. With some probability, you'll end up in state S prime. Which could be like jumping off a cliff, for example, in a game, right? So so this is just a probability object. It's just saying how the states transition, and this is an object is saying what is the expected reward that you can get. Okay. If you have these two numbers, or these not numbers, but like these two functions, right? Given these two inputs, it has to spit out a number. Given these three inputs, it has to spit out a number which is 0 and 1. It's a probability. If you have two function calls like this, which can for every state action next state, this guy, and for every state action can spit out a number, you can work with them to figure out what is the best thing to do in every round is, every time step is. Okay. Okay. This is the instantaneous reward. So in the state during this action, what's the immediate thing you could get? It could be random. That's why there's an expectation. But our goal was with the gamma thing. That's our choice of a gamma that we had.
Whatever is my environment,
Yeah.
right? It will take me some infinite number of steps.
Sure.
But when I started off, my reward is huge.
Yeah.
But with time, since I'm multiplying that value less than 1,
Yeah.
it is kind of reducing.
Yeah, that is true.
And after a certain, I'm not even sure when it will happen, but after a point of time, my reward will be too low that I might not even jump into the next state, even though I have to. Yeah, is that something that could happen?
No. So you are thinking in terms of that reward being too low from current time step. But once you've reached that time step, that reward is the highest compared to everything else that you can get. So, if I'm at the beginning of time, reward 100 rounds later is quite low because gamma to the power 100 times whatever the number I can get is kind of irrelevant while taking while I'm at time t. But once I've reached 100, all this is done. Whatever reward I collected, I already collected. At this point, this is the biggest reward. The 100th reward is the biggest compared to, let's say, the 200th reward. Okay, so it becomes, so it's like the time value of money. I don't know if you guys have taken like some sort of a finance basics course or something. So money today is more important than like the money you get like next year, right? So there's a discount factor involved. Okay, so it's very similar here. So you care about the immediate reward you get compared to the reward that you would get tomorrow or day after tomorrow. You don't have to do that. Gamma can be set to 1, which means that you care about both of them equally. Or you can set gamma to be greater than 1. You care about the reward that you get later on compared to today. So there are those variations in the literature, but for us, we'll keep it simple. So here's a simple. I mean, so since I said there's two functions, the reward function and the transition probability function. Here's the reward function. In every state, irrespective of what action, it'll always give you -1. It's a constant function. Okay? In this example, in the maze example, and the dynamics, you know, dynamics, for example, could be random. So, for example, if I'm in this state, actually, did I have that? Oh. If I'm in this state and I say go north, maybe the game engine, in this case, the maze software is such that it will not let you go north all the time. It may, with some probability, push you down. Okay, that can happen, right? So that's represented using the transition probability. So you're in a certain state. In this state, you took an action go north, but you did not end up in S prime with probability 1. Maybe you did not end up here with probability 1. Maybe with 90% of the probability you ended up here. Maybe 10% probability ended up here. It's just environment, right? An environment can behave in any way. That's all I mean. So any questions so far about like the three components, which is just a policy, a value function, which can be computed for a given state and given policy, and the notion of a model. Model is just like a description of how the environment kind of switches from state to state, and what is the reward as a function of state and action. Yeah.
Prediction of reward. We will do,
Prediction of reward.
yeah.
We are not going to predict reward.
Yeah.
I mean, ideally, if somebody tells us this object and this object, we don't. There is no learning involved. See, the model of the environment is like the forecasting model. Okay, if somebody tells you these two, then I can forecast. Oh, if I take these actions, this is the probability which will end up in some good state or bad state, right? So, a learning problem. One way to learn is to learn these two functions, and once you've learned these two functions, figure out the best action.
Is it, would it be fair to say that the transition function is a little bit, actually a little bit explore versus exploit as well? Like maybe having it not always go 100% one way or the other based on the work, but have it have that 10% to the price of the year.
The transition probability function here is not really related to what is you doing exploitation is because you don't know what these functions are. Okay, so in the reinforcement learning problem, as I said, the protocol is you try something, you get a next state, you get a reward. You never get to see these guys. So you need to explore to figure out these guys just enough so that you can collect all the rewards. I mean, collect as good expected rewards as possible. Okay, if you've already been given this, then you don't. You can just solve the problem offline. If somebody tells you gives you these functions or tells you exactly how the environment is going to behave, then you can go back to your drawing board and figure, oh, because the environment behaves this way, I should take this action in expectation, that action in expectation, for example, and then figure out the best actions that you can take, or figure out the best policy, and then actually deploy it in reality. Okay, so we are in a situation where we don't know P and R, so we have to do trial and error while taking actions. Okay, so you're taking actions to collect rewards, but you also care about learning the environment and the reward just enough so that you can take good action. So it's the same dynamics, same dilemma which was happening in the previous lecture.
And it's the popular transition one is unique for each state. Like obviously going through the maze, it can't just be 90% north every time.
Yeah.
Each one would have to be given the state, it will come up with different probabilities.
So if you're in this state, and if you take the west action, then with some probability you'll go west, and with some probability you may go somewhere else. That's all I mean. That could be the dynamics of the state. It could be dynamics of the environment. It could be that given that state, this circle state, I guess this state, taking a west action would always end up in the west situation. Then it will not be probabilistic; it will be deterministic. But probabilistic one is just a generalization of that. So the environment you don't know. So I'm just saying, if you know the environment, then those are the objects that characterize the environment. But we don't know a priori what the environment is. So if we had lots of time, okay, and if we had the ability to be in any state, then we'll try out every action and see where all we can go and learn this, right? This is just be in the state, try action 100 times, you know how many times you learn it in state S prime, how many times you learn in state S double prime, empirical probabilities, they hopefully are the same as this guy. Again, you try action 2, get into some other states, empirically estimate it. If you had a lot of time and you didn't care about collecting the total reward. Okay. So this is the model. It can be stochastic or deterministic, and they're not given to you in advance. If they're given to you in advance, it's just an optimization problem. Okay, um, we'll get there pretty soon. I'll revisit this point again. Any questions? I know so the biggest thing leap is the notion of a policy is fine because it's like a classification function goes from features to labels. Instead of features to labels, it's state to actions. Okay, so that object is fine. The first non-trivial object was the notion of a value function. Okay, it's somehow capturing, oh, given a policy, it's like the expected total reward that you can collect from that state. Okay, for a given state. So it's like the how valuable the state is, and it's encoded exactly in this definition. Okay, expectation of total rewards, and it's very looks similar to the objective of the agent actually, and you'll see that in fact that is the objective of the agent given the starting point. So to where it tries to figure out the best policy or best actions. Okay, so that was the first non-trivial object, value function. Okay, model is just a way to describe this environment where, oh, if you take this action in this state, this is a transition, this is the probability which it will go to next state, and if you take this state, if you are in this state and you take this action, this is the expected reward that we'll get. Okay, so it's just a description of the environment, how it will respond back the next state, how it will respond back the reward. Okay, so you as an agent don't have to implement that, how environment looks like. Somebody else, for example, the game designer, Doom, the people from Doom or the people, who built Atari would be the ones who will say, oh, this is how I'll give you the reward, this is how I'll tell you the next state. Okay, what you have to figure out is how to kind of play such that you can get total rewards. Okay, or win the game, for example, or do best decisions over a time horizon of a year. So for that, let's start with so the reason why I introduced those three, policy, which is a mapping from a state to action. If it's deterministic, in this case I've written it as like a conditional probability, because in a state a policy could say, oh, with some probability I don't know what to do, so with some probability go left, with some probability go right, for example, right? So that's why it looks like a conditional probability here. A value function given a policy, as I said, is the expected total reward. Okay, given, this is the expectation with respect to pi of rt plus 1 plus gamma rt plus 2 and all that. Okay, and model means these two guys. Okay, these two functions, and so we'll revisit them in the definition of a Markov decision process. And then the goal, the goal has always been to try actions so as to maximize total reward, right? I mean total cumulative reward or whatever. And that goal of finding the best sequence of actions is the same as finding the best policy. Okay, it's best policy pi. Okay, the policy pi is always saying is in this state what's the action to take. Either I can say, oh, figure out what's the best action to take, or you can tell me what's the best policy, which literally is saying in this state do something. Right? So it's the same idea. So finding the best policy is basically the idea of like optimizing for the best policy, right? So if I tell you the model, if I tell you everything, then there's nothing to learn. If I tell you the model of how the world behaves, there's nothing to learn. You just have to figure out the best policy. That's this guy. But if I don't tell you the model, still you have to figure out the best policy. Okay, that's the RL part. So the agent playing Atari game Breakout does not know the game engine, like what's the source code and how does the dynamics behave. Still, you have to kind of learn the best policy of how to move the paddle at the bottom, right? So that's what we are trying to do. So let's start with, so what's a Markov decision process? It's a useful way to describe the RL problem. And as I said at the very beginning of the class, we'll start with a simple object, Markov chain. Okay, understand what a Markov chain is through examples. Then we'll go to what is a Markov reward process, again through examples, and then we'll get to Markov decision process. Okay, so that it's very clear. Each increment will have one additional item. So that's how we'll kind of learn this. Okay, and yeah. So now let's forget about learning. Let's forget about reinforcement learning for pause that thread for a moment and just understand what is the Markov chain. Okay, Markov chain is described. A Markov chain is just a sequence of random variables that obey a certain conditional probability relation. Okay, Um, in this case, the state transition probability of going to so first of all, what is Markovian here is that probability of being in state S prime given state st is equal to something doesn't depend on all the previous states. That's the Markovian or memoryless property. So given the current situation, the next state probability of being in some other state has nothing to do with the past. Okay, that's Markovian. Markov chain just means it's like there's a state space. Okay, maybe the state is sad, happy, neutral, sad, happy, neutral. Maybe that's the only things these random variables can take. Then the state space is just three, and so you'll have a chain. Some sort of like a transitions that can be graphically represented. Okay, it's like it looks like a chain, so or a simple graph. So anyway, so in a Markov chain, the state transition probability, let's assume that it's represented as this. Okay, P as S prime. Remember now we've dropped the notation A here because now we kind of stepped back a little bit and want to understand a simpler object, which is just a Markov chain. We're just trying to understand how the environment autonomously states changes from state to state. Okay, for now, for this and the next slide. So this guy is a function of two things. What's the current state? What's the next state? Tells me what's the probability of me going from current state to next state, right? So that thing can be written as a matrix actually. Okay. So matrix is going to be, oh, you are in state S. What's the state S is equal to 1? What's the probability of me going to remain in state S is equal to 1? Okay. Or if I'm state S is equal to 1, what's the probability of me going to state S is equal to n? Okay. So that's the matrix representation where each row has to sum to 1. Because from a state 1, I have to go to some state. Either stay in state 1 or state 2 or state 3 or state n. But I have to go to somewhere. Okay. So that's why the row sum is 1. Sum is equal to 1. Okay. So yeah. And here's an example of a Markov chain. Here some, the nodes are of all shapes, but don't worry about the shapes of the nodes. It's basically the state space. Okay. So each random variable st or st plus 1 can take any one of these things inside a box or a circle. Okay. So just think of it this way. So if I'm in state class 1, then I can either go to class 2 or I can do Facebook. Okay. Those are the only two state transitions. The other states that I can get to, other state values that I can get to are 0 probability. So here's some episodes of, this is called a student Markov chain from this reference. And so let's say we pick always starting point as S1 is equal to C1, as in the first state is always C1, class 1. Then if you sample some episodes just means some sequences from the starting state S1. Okay. Then here are some episodes. You start from C1, go to C2, C3, pass and sleep. Okay. You see, if you get to sleep, there's no way to exit and do something. Okay. This is like a terminating state. Okay. So in that probability, if you think of the probability transition matrix, from the sleep state, there's no exit. Okay. You stay in sleep state all the time. Okay. So sleep to sleep is 1, everything else is 0. So these are, yeah.
I was going to ask, is hidden Markov models, is that completely different, or is this like a tangential subject, or same thing?
No, hidden Markov models, the hidden variables are going to be a Markov chain. Okay. So hidden Markov models are also observable random variables. So let me just, don't have it. Yeah, hidden Markov models. Think of it this way. So there's only 3 states, okay, for simplicity. Okay, and then maybe something from here, maybe something from here. So every state can go to every other state, every state value. Okay, so let's say that my random variables, let's call them x1, x2, x3, and so on. Okay, each xi can only take 3 values: a, b, and c. Okay, this is a, this is b, and this is c. And what these arrows represent? Let's say arrows are all 1/2 each. All they mean is that the probability of x2 given x1 is equal to, let's say, a, x2 is equal to a. Oh, there is no self transition, is 0. Probability of x2 is equal to b given x1 is equal to a is 1/2. Probability of x3 is equal to b c, sorry, x2 is equal to c given x1 is equal to a is 1/2. Okay, so this is a row in that transition probability matrix. So one, like the row is just a, you are in state a, you can go to a, b, or c. So that's 0, 1/2, 1/2. The row sum is 1. Okay. Now, what is the hidden Markov model part of it? Is that, oh sorry, c should be here. This is not c. Okay, the outside thing is not c. Now, so how many of you are kind of confused even at this point? Is this fine? Okay, so hidden Markov model is saying that in any, so the way you will draw that hidden Markov model is basically you'll say x1, x2, x3. So what does this represent? It's a different graph than this. Okay, this is a state space graph. It's saying, oh, state values and how do you jump around with state values. Okay, so any of the x1, xi's can take any of these three values. Here, there's a slightly different graph where we're showing, oh, x1 influences the value of x2. And that we know that because given x1, there's some probability of me being in x2 being these three. But if x1 was not a but b, then it would be different probabilities of. So let's say x1 was b, then these numbers would be different. So that's all this means. That if x1, given the value of x1, there will be some values of x2. You know, this conditionally dependent. Okay, so x2's value depend on x1. X3's value depend on x2, but they don't depend on x1. That's the Markov property, hidden Mark. So now the hidden part is that you actually don't see these random variables. Okay, so if you generate data from a hidden Markov model, you only get to observe what is called a observation random variable at every step, y1, y2, and let's call it y3. So you only get to observe some value, okay, which is not the original guy. So that's why you call it the hidden Markov model. This is Markov in the sense x3 only depends on x2, x2 only depends on x1, and not everything else before. And that's Markovian property, hidden because you don't get to observe the realizations of these random variables. You only get to observe some other random variables. This arrow just means that this random variable only depends on this random variable. Okay, this random variable only depends on this random. So that's a hidden Markov model. Okay, but most importantly for us, this is let's focus on just this guy. This is a Markov chain. This sequence of random variables follows a Markov chain. Okay, for simplicity. And so this is some sequence of realizations of that Markov chain starting from C1. So from C1 we went to C1, C2, C3, pass and sleep. Okay, in one particular sample. Okay, one particular sample path. And similarly, you have these other guys. Okay, and here in fact they've drawn the probabilities with which you can go to. Like for example, class 1, you can go only to class 2 and class or Facebook. You will not go anywhere else. Okay. So that's a Markov chain. Is the Markov chain clear? So there's some nice things about Markov chain, but we will kind of skip that. About something called stationary distributions and things like that, which are kind of relevant for sampling. Okay, so we'll probably revisit Markov chains when we talk about Gibbs sampling again. So some of you have seen Gibbs sampling in 575. So we'll see Gibbs sampling again, and we'll talk about Markov chains again. Okay. So for us, all that we need for now is that there's this transition probability matrix, the script P that I wrote before. This is script P. Okay. And any number here, for example, is script P. S prime S or whatever that symbol was. If you are in C2, what's the probability of going to C3? And so now let's move one step forward. We know what a Markov chain is, just the transition probability. It's pretty much determined by the script P. Now we're going to add two more things. Okay, so Markov chain, actually, I forgot to mention, is represented by these two tuples. It's a tuple. Tuple just means a collection of two things: states and how do you jump across states and how do you jump across states. Okay, the script P is literally saying how to jump across states, right? Now we will add two more things: script R and gamma. Okay, so this is going to be called a Markov reward process, where S is the same as before, states. P is still the same. Okay, still the same. Okay, it's given in state S. What's the probability of going to S prime? Okay, and now two new objects which are in red are as follows. Script R is basically saying, oh, you are in state S, here's some reward for you. Oh, you're in state some S prime, here's some reward for you. Okay, so it's just an emitter of some number. Okay, and every state just gives you some number. Okay, so that's the reward function, and gamma as usual is a discount factor between 0 and 1. Okay, so that's a Markov chain with rewards. And once we have Markov chain with rewards, we can already talk about something called return random variable. Okay, a return random variable GT is just going to be, oh, in Markov chain we jump across from state to state, but every time we jump across from state to state, I keep realizing some reward. Okay, let's call that reward RT. Oops, RT plus 2, RT plus 1, RT plus 2, and so on. So basically some like this, right? If I keep jumping across state from state, and in every state I get a reward. So the sum of all those random variables discounted with some gamma stuff is called the return random variable. It's just sum of bunch of random variables, right? There's an infinite sum going on, but modulo that, it's just a sum of random variables. And because there's a return random variable, its expectation is what I'm going to call as the value of that state. Okay. So the value of a state is the value function is nothing but, I mean, it's basically the long-term value of the state is basically the expectation of the return random variable starting from the state little s. Okay. So you have the Markov chain. I said now we start emitting rewards. All I'm saying is, oh, if you are in some state, take the expectation of emitted rewards, sum of the emitted rewards. Okay, that's GT, return random variable. Take its expectation. That's the value of that state. Okay, if the value is high, that means that from that state you're jumping on is going to be valuable compared to in some other state jumping through the Markov chain. Okay. There's no prediction here. The Markov reward process is given. Yeah. Oh yeah. So value is like some sort of encoding or not encoding, but some sort of summary that this state is valuable because in expectation you'll be going into other good states where you'll also get high rewards. It's not it's not a prediction as such, but it does capture that future value of being in the current state. Essentially, it's like this is a highly desirable state because from this state, in expectation, you will collect lots of rewards. Okay, for example, if its V is high.
It's the sum overall of the future possible states.
Yeah. So these are all. So from the current state GT, I'm in state S. I can, these are different realizations of these random variables that can happen, right? So GT can take 100 different values. Its expectation is going to be a summary of how good that state is, and that's what we're calling as value of that state. Yeah, but there are many trajectories. Right? If all these guys realize some numbers, there could be many different values, but you're going to do this discounted sum. So now you'll have many GT values like a histogram. Take its average, and you get some number. Yeah. Yeah, here there is no action, so something is happening autonomously. In Markov chain, there was no control, right? We're not doing anything. I mean, the thing is just jumping around by itself, like according to transition probability matrix. Now it was jumping around by itself, but in addition to it was emitting rewards. Okay, so we are just saying, oh, it's jumping around by itself. There's already dynamics already defined. It's already reward process already defined. Here's numbers that I can compute. A summary statistic for how good a state is. Okay. Now we'll map it back to our problem pretty soon. Okay, next slide maybe. Yeah.
Can you initialize the sort of model? Do
Yeah.
you have to give it some sort of assumption of how many states there are, or can it just sort of
Yeah.
adding states on its own?
Now for now we assume we have a fixed number of states like 100, 1,000, or 2,000. But you'll see that that doesn't make any sense if you're like even playing the breakout game. The number of screenshots is like so many, right? I mean, you can have a screenshot where the brick is over here, a screenshot where there's different brick configuration and so on. So that can be relaxed. Okay, state space being too large is not an issue. But for now, we're just discussing a finite number of states. Okay, a finite number of values that the state ST can take. random variable can take for now, but we can relax it pretty soon. Um, so here's the reward process. I mean, it's the same as before. So few strings like this, where the Markov chain is jumping around from starting state class 1, class 2, class 3, pass sleep, class 1, Facebook, class 1, class 2, pass of the sleep. I mean, sleep is what's terminating. Okay, from sleep we cannot really do anything more. And now what I've written here is that, oh, you're in class 1. So here it turns out the reward is not. So as I said, there's a reward getting emitted every round, right? So every state, right? So if you're in this state, there's an R number which is always -2 instead of being random. At class 2, there's an R number which is always -2 instead of being random. Okay. So so you have a bunch of R numbers, right? So this one, a reward number, sorry, at every state, and you just do a discounted sum, okay, in every trajectory, okay, and you get a bunch of numbers. You can take an average of this, and that will be some sort of an estimate of the value of that state C1, okay. Just some numbers to show that, yeah, I mean, you can compute this in really small state spaces. Here the state number of states is just 1 2 3 4 5 6 7. It's just quite really small. I mean, it's not really useful.
And at this point, it's not using little words for anything. We have to
Yeah.
find-
Yeah. So we just graduated from Markov chains to Markov reward processes. Now we'll start bringing in control, and so we'll bring in control, and then we'll also bring in learning, because we now need to learn these transitions and rewards. Okay. Okay. So before we even talk about control, there's one more thing that I want to show. It's a nice, trick to see here rather than later. Is a trick about recursion. Okay. So we know the value of a state is just the expectation of the return random variable given the starting state, right? Given the starting state is s. This s is the same as this s. And now, but we know what GT is. GT is RT plus 1 plus gamma RT plus 2 plus gamma square RT plus 3 and so on. Right? Now comes the fact that we can take a gamma common. Okay, there's gamma square, something else, gamma cube, and all that. Take gamma common, then you have RT plus 2 plus gamma RT plus 3 plus gamma square RT plus 4 and so on. Okay. So taking gamma common is fine, not a big deal. Okay. Although it's an infinite sum going on here. Okay. Now the cool part is that the thing inside RT plus 2, RT plus gamma RT plus 3 and so on is actually the return random variable from T plus 1 onwards. This thing in the bracket is the same as GT definition at T plus 1. Okay.
Figure this out.
What is it? You can just unroll it and figure it out. I mean, okay, so it seems kind of alien to us. It seems like a difficult trick, but people, there's a branch of mathematics where literally people work on sequences and series. So these types of tricks they kind of employ. So if you use arithmetic progressions or geometric progressions, you would kind of do these types of tricks. Okay. I think in high school people do APGP, so AMGM type of thing. Sorry, progressions and series, sequence and series. Anyway, so you can call it GT plus 1. Okay. So up to this point is fine. But the last line, what's happening is we can push some expectation inside. Okay. So what do I mean by that? So this expectation, remember, this expectation is with respect to everything that can happen in the future. Okay. Right? This expectation is saying, oh, with this probability you'll get to this at this location or this state. From that state, so some probability you'll go to some other state and so on. So there's a lot of probability, like a product of probabilities happening with this expectation. You can send some of it inside, as in, so this, like, think of it as the expectation with respect to the first random variable, expectation with respect to the second random variable, expectation with respect to the third random variable. Everything is summarized here. I'm just trying to push all the expectations inside except for this guy, because this one, is a random variable, so that expectation is still outside. But this is not this. This is all the expectations with respect to RT plus 2, RT plus 3, RT plus 4. Everything has been captured in this value function. Remember, what is V of ST plus 1? Is the expectation of GT plus 1, right? So let me illustrate that by example, and we can take a small break. So all I'm saying is, what is it? So V of S, there's an expectation, right? of RT plus 1 plus gamma GT plus 1 given ST is equal to S, right? Something like this is what we did with the expanded recursion, took the gamma common, we saw, okay, these are all R's, just call it GT plus 1, right? From here, what's happening? So this expectation is actually, okay, expectation with respect to R t plus 1 and the expectation with respect to R t plus 2 onwards all the way to whatever infinity, whatever R t plus infinity, R subscript infinity, for example. This expectation is what I'm saying. Oh, with respect to this guy, this is a constant, right? Because RT plus 1 has nothing to do with expectation with respect to RT plus 2, sorry, RT plus 2 to infinity. Okay. So this expectation is what I'm trying to say, that you can push it inside and bring a bracket in front of this. Okay. Is this trick alien? Is this fine? Okay. So this expectation with respect to RT plus 1 still remains of RT plus 1 plus gamma. That's why you can substitute it as V of ST plus 1 given ST is equal to S. When I write RT plus 1, I'm not saying it's not the randomness. So RT plus 1 is random, but also the next state that you get to is random. Okay, ST plus 1. Okay.
Apart from this being kind of an interesting thing to do, is it make it easier to figure out what the B is later?
Yes, so this is so the reason why I'm spending some time on this is that this is a basis for huge class of algorithms. The Q-learning stuff, I mean, all the algorithms that we see here, they are iterative in nature, but they kind of work with this equation. And this equation is the, I guess, the precursor for what is called the Bellman expectation equation. Okay, and that's the precursor for Q-learning. Okay. So if you directly jump to Q-learning, you'll say, oh, some equation going on. If I iteratively update, I'll kind of learn the best thing to do in every situation. But that's like seeing the final result, but something went on to get to there. That's what we're seeing right now. Okay. I mean, so you ultimately, in terms of coding, you'll just implement Q-learning, and that will kind of take care of not this value function itself, but slightly different value function. We'll talk about it soon. But how did we get there? How did the algorithm come out? Is what we are trying to learn right now. So yeah, so for us, for Markov reward process, all we're trying to say is that there's a recursive relation between Vs and Vst plus 1. Okay. Actually, there's a nicer form. I should have written it before. So that's the same equation from last slide. Okay. So let's understand this picture, and this equation is the same as that equation. So here it looks like something is hidden. Here, let's look at this one. Okay. So what's going on? So value at a given state S, okay, is the average reward that I can collect at the given state S. Okay. Expectation with respect to RT plus 1 is just this, R of S. Okay. And then gamma is the same as before. V of ST plus 1, this is random. So I'm going to take an average. Okay. V is an average, right? Average over. Okay. I should write it this way. Yeah. So you're in state S. So you're in state S. So let me highlight that S guy here. You're in state S. The second term is saying I may get to state ST plus 1, which is random. Okay. So what are ST plus 1s? There could be many different S primes. Okay. It could be S1, S2, S3, S4 that I can get to from S. I'm just saying, oh, what are all the states you can get from S to S? From S. Okay. From S you can get to S prime, S double prime, S triple prime. Okay, there's some probability which will get there, and from that, with that probability, you also multiply the value of that state. Okay, so that's what this expectation means. This expectation here, the first term is easy; it's just a reward as a function of S. The second term, gamma is as it is. The second term is expectation with respect to this. Is all it's capturing is the probability which I'll get to ST plus 1. Okay, so this ST plus 1. All the options, I'm just writing it as this guy can be all these different states. There's a probability with which it can be of there's a probability with which it can be all these different states, and so I'm going to take an average. So this is just the average of this expectation on this guy. Okay. So pictorially, let's understand what's going on. So what does this notation mean? It's just saying at this look. So this is a graph which is trying to kind of show this computation pictorially. Okay. What is it trying to say is that, oh, think of a function that I want to compute. It's given an s, produces f, v of s. That's what my left hand side is. Okay. Some number. So this graph is trying to say, oh, that number is going to be r. This r is just this r of s. Okay. Just a slightly different notation, but there's some intermediate number. And then these two bars and two circles just represent an averaging, okay, of where will I reach next? Okay, from the current state S, I could reach S prime, S double prime, S triple prime. There could be different states I could reach from the same thing. Whatever those numbers are, B of S prime, I'm going to average it. That's what these two double bars and two circles kind of represent. Okay, you're just saying that, oh, if you want to, so that it's just trying to capture pictorially a recursive relation. It's just saying that B of S and V of S primes, they're related by this equality here. Okay. So kind of we'll see this again and again. So maybe it'll solidify. But this was a new component from we have not seen so far. So of course you will face some friction. Um,
So even in the final equation, it would again be a next recursion of the gamma because ES prime would again be written as the first equation.
yeah, you can expand it and you'll get the original thing. But we don't want to expand it out.
Keep on going beyond.
Yeah, if you expand it, you'll get back the original thing, which is what we wrote in the first slide. I mean, to last slide. Yeah. The reason why we wanted to write it is because we'll get a system of equations. So if these are unknowns, unknowns are related to unknowns. So something like a system of equations is what you'll get. Uh, okay, so let's take a break for 5 minutes and resume. Okay, at 8:15. And in the meantime, I'll show you the next image.
I appreciate you. The girl. Yeah.
Just give me 1 second. Okay.
Need some juice across all that. Yeah, I gotta say this stuff if it's like anything else I've done so far, you know how to code it. You kind of need to be able to explain what's going on. Anything in the middle is just nice to have.
I'm glad you stopped him and asked what was going on in the equations in one of the slides before.
Oh yeah.
That was going on in just experience.
Oh.
That was I was trying to not understand.
Yeah, it's just we go at light speed and these concepts are.
Yeah, they're not very easy to.
Well, I feel like individually none of these concepts are that hard. But
Individually, it's just basic probability. I was just thinking that to myself. It's like final I was like, individually, I can understand what's going on. Can you connect and draw the big picture? Not yet.
yeah.
But I can know, okay, this probability, I get the matrix, I get this. Okay,
Sure.
how do you put it all together?
Yeah.
That I'm finding that hard. I know.
It's funny, I think all of us would probably more easily understand the Python code than we would understand like the mathematic notation.
Easily, yes. It's easy to understand Python code. Math is just not easy.
never take those. Do you get them?
I know. But no here makes me.
Oh, really?
I knew there was nothing already. They just didn't have them.
Yeah, I mean, that's all. It's not because this is boring. This is interesting, but
Just about all of our classes are boring in some aspect, but interesting if you think about it.
well, it's just this is fatiguing because it's 2.5 hours of it, hardly any break, and it's heavy stuff. You really concentrate to understand it.
I don't walk in and just stick with it. That's why I'm working my way and classes.
Well, I'm going to be hitting a YouTube video to try and figure out the rest of this lecture. Take care.
Simulation stuff. Let's get on the simulation. This one. So this is from CES 2017. I'm sure now it's much better. So it's basically
Quick question in the previous class.
Yeah.
So I was looking at videos for Thompson sampling and MAB.
yeah.
And they said
You're
that,
getting recorded, but it's okay.
Oops.
No, it's okay.
No. So I wanted to know. They said that Thompson sampling has a better. The regret bounds are lower for Thompson sampling as opposed to just pulling the arm in MAB. I just want to understand why.
No, they're better than uniformly at random.
Sorry,
Sure.
UCB.
No, they're not better than UCB. They both are.
Because in multiple sources, I just one there was some IDM.
I mean, maybe empirically they may be better, but in
Right.
terms of guarantees, theoretical guarantees, they're not.
No, empirically they showed that the regrets for
Sure.
this was lower than UCP, but I was not able to intuitively. I was not able to figure
Intuition
out
wise,
why.
there's no.
Like when you look at the procedure for UCP and the procedure for the other one, I wasn't able to tell why one is just better than the other.
No, it's not because the theoretical guarantees only tell you it's the same.
Okay, so there's no reason for one to think that the regret bounds are lower for Thompson as compared to UCB.
Maybe there's some intuition, but it's not encoded in the formal claim that one is better than the other.
Okay.
Okay, so let's resume. So this, I think I was flashing it for a few minutes. Before this was actually, I think earlier this year, there was this demo by Tesla about like somebody going from point A to point B, hands-free. Okay. And it's pretty cool. I mean, cool to watch. It's, I'm sure it's very scary to be sitting on a chair, not touching the steering wheel, but uh, it's good. So what's the purpose of me showing this is that a part of this technology is relies on some sort of reinforcement learning or some sort of policy learning. Okay, maybe not the whole thing, but there are parts of it which kind of use reinforcement learning. Okay, in fact, if you have a good simulator of the real world, you can actually just reinforcement learn the best controller for your car to drive. Okay, but you don't have a really good simulator of the real world, and that's where there's actually research threads called sim to real or something like that. Sim to real just means learn something on simulator and deploy it in real world. Hopefully, it works really well. So you want to have a high quality simulator. Anyway, so let's come back to the underlying object. So now we are ready to think about a Markov decision process. Okay. Um, actually, yeah. So now we are ready to think about a Markov decision process. So what's a Markov decision process? There's one more addition now, which is the set of actions. So this is a new addition. So think of a finite set of actions like the joystick actions. Maybe there are 4 different directions that you can do, and maybe a few button presses that you can do. Okay. So now this transition, the transition probability matrix or the transition probability function is now back to the original thing that we were doing 10 minutes ago. Now script P is a function of state, next state, and the action that we took. So A and S are in the current situation, and because of these two, I get to the next state S prime. Okay. And reward again is also now a function of action. So instead of previously reward was just a function of state, now reward is a function of both which state you are in and what action you took. Both little s and little a. Okay, that's the expected. That's the reward function. That's the only change. And with that, so now the picture is slightly different. Okay. So here, think of states as being A, B, C, D, and E. Okay. So states have, I mean, I've just changed the names of the states. Now your action is going to be, oh, if I'm in state A and I take a Facebook action, which means that I opened up Facebook. Or if I'm in state A and I took a study action, which means I went to state B. Okay. So now your actions are do Facebook, do study, do sleep. Those are your actions. And because in state A you took the study action, you get a reward of -2. But if in state A you do Facebook, you get an instantaneous reward of -1, which means that doing Facebook is better than locally doing Facebook is better than doing studying. Okay, but and then you go into some state where if you quit Facebook, you get an instantaneous reward of 0. Okay. Uh, yeah, and then there's also a state called pub, which can only get to after doing a lot of studying, study, and then you can potentially transfer to the pub state um, with a reward of +1, which is even greater. So anyway, so that's a change.
Question.
Yeah,
So we're not considering the probabilistic transition from state to state anymore?
there is, right. The probability I'm not showing, it's similar to the previous thing, like maybe 0.6, 0.4. Oh, okay. Oh, why am I not showing that? Good question. Actually, I should not have written that. So let's drop this. Yeah. So here the state transitions have changed. They are not probabilistic anymore. If I'm in state A and I take an action study with probability 1, I'll go to state B.
But here on A, there is only 2 actions you can take, but they don't have specific probabilities.
Yeah, there's not probabilistic. If I do Facebook, I'll actually do Facebook and go to some state D. Okay. Slightly different. I think there is a probabilistic action. So once I go to pub, I don't do anything, but with some probability I go back to study, or this way.
That's kind of the transition to the next state. I mean, next round.
Yeah, next round. So these are probabilities, and these are all. So wherever it's R, it's the immediate reward. Wherever there's no like these sets of numbers, there is no stochastic transition. So what did we introduce? We introduced the notion of actions, and therefore we can now bring back the notion of a policy. Okay? So what is a policy? A policy is nothing but a probability of taking some action in some state. So if I change, so if there are three states, um, little s1, little s2, and little s3, and in this one, like policy, like the first policy, like let's call it pi1 of a given s, can say, oh, in this state always take action x, in this state take action y, in this state take action x, and policy pi2 of a given s could be in this state with 1/2 probability take x, with 1/2 probability take y, and so on, right? So this is just a description of two different policies, okay, this one and this one. So policies are nothing but, in every state, what should I do? That's what they encode. Okay, those are just functions. Just like in every feature vector, what's the label? That's encoded by a network or whatever, some function, right? And so basically, a policy fully defines the behavior of an agent. So if somebody says, "Oh, here is a policy. Now interact with the environment," the agent doesn't have to do anything. No learning, nothing. It keeps applying the policy. It finds a new state, keep applying action. Get to some other state, keep applying the policy, and so it'll collect some rewards. Okay, and okay, so in that sense, there's no control. So if the agent is given a policy and it has to interact with the environment, there's no control by the agent itself. So in other words, an MDP is just a Markov reward process for a fixed policy. If I already give the agent a policy, the agent doesn't have to do anything. It just applies pi of s every state. So there's no control, and therefore it's just a Markov reward process, because it's literally saying, oh, in this state, I already know what action I need to take. Given that action, I know exactly. I mean, the transition probably tells you which state you go to. So there's no, you're not manipulating anything. So that's a Markov chain, okay, and you get rewards emitted because you took a particular policy. You fix the policy, and therefore, and that is a Markov reward process, okay. So state sequence is a Markov process, as in, so p subscript pi just means that I fix the policy to be pi. Okay. So actions, I don't have a freedom to take actions. And r subscript pi means, again, the same thing. I don't have freedom to take an action. So it's just whatever the policy suggests as the action, that's the action I'm taking. And therefore, that policy suggested action and the state emit a reward r, script r. Okay. So, and the state and reward sequence are called, is essentially Markov reward process. Okay. So that's a good thing, because okay, so before I continue, so here's the relation between the MDP's the state transition probability function and the reward function, and the Markov reward processes state transition function and the reward function. Okay, all it's saying is, so here we are assuming stochastic policy. So we are just saying, oh, you're in state S. There's all these ways you can go to state S prime. Okay, maybe you take action one, action A1. You could go to S prime with some probability. You take action A2. Maybe also you'll also go to state S prime with some probability. Add them together. Okay, that's what we are doing here. What's the probability you'll take those actions, and if you take those actions, what's the probability you'll end up with the same state S prime. Okay, so it's just a relation between the Markov addition process objects and Markov reward process objects. Okay? I mean, Markov addition process objects and Markov reward process objects, which are p subscript pi's. Okay, so this pi over what is it called, above pi is basically saying it's a Markov reward process. So now let's revisit value functions. So what's changed so far? Before the break, we had talked about value functions for Markov reward processes. After the break, we said, oh, now let's talk about the policy pi. Okay, but if the policy pi is fixed, then it's again a Markov reward process again. So now let's go back and talk about value function again. Okay, but now we're going to call it a value function subscript with the subscript pi. Okay, so that's the fixed policy pi that we gave to the agent, because of which it became a Markov reward process, right? So for the state, it's called the state value function v pi of s, and for an MDP is this quantity. Okay, so nothing has changed except the subscript has changed to pi, because now we have fixed the policy, and because of the fixed policy, it's a Markov reward process, and so everything else is the same. The return random variable, the expectation of return variable is the same. Okay, so that's the state value function in the MDP world for a given policy pi. Now there's also going to be a new value function that I'm going to introduce, okay, which is called the action value function or the state action value function. Okay, so now this is the second delta. So value function was new already. There's a second type of value function. It's called the state action value function or just the action value function. We're going to call it q pi of s comma a. Okay, so what's the difference between b pi of s and q pi of s s comma a? Is just that it's the same return random variable. It's the same. I mean, the policy is fixed, so it's the same policy. Except when I'm in state s, I'm not gonna directly apply pi of s first time. I'm gonna let that a be my choice. Okay. So the first, when I'm in state little s, a is my choice. But the moment from little s, because I took a action little a, I get somewhere. From then onwards, I'm gonna apply pi. Okay. So it's like, let me write it here. So v pi of s is saying it's basically reward, right? Reward in state s and taking pi of s plus all the places that I can get to because I was in state s and took pi of s, right? I went to s prime. It's s prime in s of v pi of s prime. Okay. So is this is just saying, oh, because you told me what pi of s is, this is the reward I'll get immediately. And then because I took an action pi of s in state s, I'll get to s prime with some probability. And there's many such s primes that I can get to. And for each one of them, I'll take the b pi of s prime at that location. Okay. Now the difference with q pi of s comma a is nothing but script r s a. Okay, a is something that I get to choose, so it'll just change the first guy. Plus, once I took that s comma a, again I'll get to s prime, which is p s and a s prime, and then from s prime onwards, it's just a value of following that policy pi of s prime. So here is where pi comes again. Okay. So it's just one step delayed. Okay. Here I'm still getting choose an action and then kind of applying pi forever. Whereas here I kind of apply pi from the beginning. Okay. That's the difference between state action value function and value function.
Why would you need one if you have the other?
Yeah, both are related to each other.
Right, they're-
I'll show the relation pretty soon. Yeah. I mean, why do we need two different definitions? Is because
Your action is just a result of your policy pi.
no, this action now is a free variable. So the difference between these two is that I'm going to use policy pi, but in the first time step, I get to choose whatever policy I can, whatever action I want. Okay, that's why there's more degree of freedom than this. In this guy, if I just apply instead of a, I do pi of s, and this is the same as that, right?
So this is actually a summation of immediate reward and the long-term reward.
Yeah, this is the immediate expected reward, the first terms in each of these equations, and next term is saying the continuation cost, right? I mean, this is basically from that new state s prime, what's the value of that state value of the state. Actually, I can again recursively change this into q pi, but I will do that maybe a couple of steps later.
So the immediate reward actually it kind of depends on that state only. Where we
Yeah, immediate reward depends only on that state and the action that I took in that state.
previous coming to that state or actually to the observation.
Oh, okay. So I'm just saying that you are in ST, you took an action AT, and you got a reward RT plus 1, and you also got next state ST plus 1. So this RT plus 1 expectation is what this guy is. So this guy is S, this guy is A, RT plus 1 is that script R subscript S comma A in my notation. I mean, in different books, you'll see it's different notation, but here at time step T, you are in ST, little s, you take an action capital AT, which is little a, and you get a reward capital RT plus 1. That's a random variable. Its expectation is the script R S comma A. Okay, so we are running a little bit late, but let's move forward. Okay, so that's state action value function. This is a definition. It's again the expectation of the return random variable. Okay, and which is what I expanded out. So this is what I had written. I think in that slide, And the action value function, as I said, can also be similarly decomposed. Okay. In fact, the action value function is q pi of s comma a is the expectation over pi of the first part is the same, rt plus 1, plus gamma q pi of st plus 1 comma at plus 1. Okay. So did I write it correctly? Okay, let's actually, I mean, in this notation, it's kind of a lot of things are hidden. Let's actually see the next slide where we'll see the exact decomposition. So, I mean, so before we focus on the graph, on the picture, which I'll explain again for this situation. So q pi of s comma a is just saying, oh, I have 1 degree of freedom for now. So I've been given pi and I've been given a. So r of sa is the reward for taking action a. And because of action A, I can get to S prime, right? That's all these potential S primes that I can get to. So that's why there's a summation. That's the expectation with respect to that. Now this guy is actually equal to V pi of S. Okay, this is nothing but V pi of S prime. Okay, if you remember, I think that's what I wrote here. All the S primes that you can get to, given these two actions, I just wrote V pi of S prime. In that slide, we expand out what's the relation between V pi of S prime, yeah, V pi of S prime and Q pi of Q pi. Okay. So V pi of S prime is just saying, oh, what's the value of a state? Oh, if there are 10 actions to take, average out the 10 actions of based on what's the policy telling you. Okay. That's this guy.
But over here, we are not following any policy.
We are. I mean, so at this point, we are supposed to follow policy pi. At this point, we are not supposed to follow any policy for the first step. But from here onwards, we are supposed to follow policy pi. So that's why this a prime is going to be what is policy pi recommending. At S prime, policy pi can be deterministic. It can say exactly one a prime, then it will be pi of S prime. But it can also recommend several ones, and that's why there's an averaging with respect. It's a stochastic policy here. But if you think of a deterministic policy, instead of summation, this will be gone, this will be gone, this will be q pi of S prime, pi of S prime. Okay. So it's as if saying q is basically just v pi of S prime. That's what I mean. Okay. So why do we? I mean, so again, back to Scott's question. So why are we doing this? Is because these recursive representations help us solve for the best policy. If you know the model, which is not reinforcement learning, there's no learning here, just to optimize for the best policy. Or if you don't know the model, also this equation lets us design this Q learning algorithm. Okay, is the intuition behind the Q learning algorithm. So what is the problem? So remember at the beginning of this lecture, we said we want to maximize the total expected reward. Okay, so RT plus 1 plus RT plus 2 all over, but we said that is actually equal to V pi of S. So that summation, if I fix a policy, there's some summation for some rewards I can get for a fixed policy. Now, then the agent's problem can be just written as maximize over all policies that they can maximize this V pi of S. Okay. So that's called the optimal state value function. So I'm just defining the optimization problem here. If there was a way for every pi, if there was a function or a black box which would tell me for every pi, V pi of S for a starting state S, okay, for some state S, then I would figure out, different pi's give me different values. What's the pi which will give me the highest value? We know that V pi of S is the expected total return, right? So that is exactly what we want to find. So if you maximize our pi, whatever is the value, that's V star of S, which is called the optimal state value function. Okay. Now you may say, if I change states, there will be different V star of S1, V star of S2, V star of S3, but you can actually get the same policy. Okay. So starting state doesn't matter. That I'm not showing here, but yeah. So this is the optimization problem we care about. And similarly, if we have just the state action value function, it's the same thing. It's the same max over pi of q pi of S coming. It's still the optimal. I mean, this guy is called the optimal state action value function because two things are fixed. Okay, S and A is fixed, and I'm asking from If I fix these two, for every pi, there's some score that I can get. And so for fix these two, whatever the best policy it is, this number corresponding to that is called the optimal state action value function. Okay.
So this new policy will give you the like optimal value for every state.
Yeah, there's a pi star. Yeah, there's a pi star. It turns out that because we're in infinite horizon case, it doesn't really depend on the starting state. Okay, for example, here, it's the same pi star. Okay. Yeah. So now what we're going to do is look at what is called the Bellman optimality equation. So far we have seen Bellman expectation equation, which was the recursion form. Now also we'll have the recursion form, but let's directly look at the Bellman optimality equation for q star of s comma. It's an equation which is only relating the q stars, q star or v star, okay, which is the optimal state action value function. So the optimal state action value function is related to the immediate reward plus the usual gamma times the sum over all the next states that I can get there. But instead of now q star of s prime comma pi of s prime, which was specific to a single policy, because now we have the optimal policy, we're going to substitute it with the max. Okay. So there's a max operation going on because we have the optimal state action value function in this equation. So we are saying that if we had if we had access to this function for every state comma action pair, it would follow this recurrence equation. Okay. Yeah, so the optimality just comes from the fact that this max operation is going on, and so this equation holds for the optimal value function. So if you care about solving for the optimal value function, then you just have to solve this equation for every state action pair. So q star of s prime q star of s comma a is unknown, so maybe there are 10 states and 2 actions. So every state 2 actions, then how many, like 2 to the power 10 such pairs, so 2 to the power 10 such equations, 1000 equations, you can solve it. Okay, but you can solve it, but there's a twist because there's a max operation. It's not a linear equation, linear system equation, but otherwise you can solve it. Okay. And I said I'll tell you this notation last time, but I kind of skipped. So this notation just saying that if you're in s comma a, there's an immediate reward, and I'll get to s prime. So these are the different s primes. Take an average. So this average is basically this thing, and then this bar over here is saying take the max. Okay. So it's like a pictorial representation for. So just saying q value, state action value at a given pair is related to the immediate reward. That's this guy, plus because there's two white circles represent states. Okay, and because there was no bar here, no bar here, it's like an average over all the s primes. So that's what average of s primes is. And then below it's related to the immediate reward, and get to this s prime, and at s prime you take the max over a prime. So that's max over a prime is this dash over here. It's just like, don't worry about this if you don't follow this graphical notation, as long as you understand this equation. This graphical notation saying is that q value q star at this location dot is related to q star at s prime a prime. Okay. That's all it's trying to capture. So anyway, that's Bellman optimality equation. And if you have the q star of s comma a, then what is the best policy? There's a one-to-one. So if you could somehow tell me the value function, state action value function, best state action value function, then I can tell you what the best policy is. The best policy is going to be just greedy with respect to the q star of s comma a, which just means that, okay, in state s there are 3 actions, a1, a2, a3. For each one, if I know q star of s comma a1, q star of s comma a2, q star of s comma a3, then just take there are 3 numbers basically. Take the action which is giving me the highest number. Okay, so whatever that action is. So pi star, which is the best policy, is just that action with probability 1. So pi star is not even a stochastic policy, it's a deterministic policy in this situation. Okay, but not always the case. Here there's some assumptions like infinite horizon, discounted reward, and so on. So that's why this is the best policy. Okay, it's deterministic policy. It's just take the max over the state action value function, the best state action value function.
What was the average function like the last equation breaking it over?
This averaging, this is always the case, right? Before.
So you just take an action, go to all these states,
Yeah.
average it out.
No. So this equation is just relating q star of s comma a with other q stars of s comma a's, and the relation is just as before, right? So what changed is actually this box here. Yeah. Otherwise, it was the same as before.
So, but I'm trying to understand you like layman terms that
Yeah.
when we say a value, you said two x. So let's say we have two x's.
Yeah.
Okay, so we take the first action, we go to the state.
Yeah.
So we are kind of average. What are we averaging about?
So there's a picture somewhere. Yeah. Let's look at this. Okay. Uh, so I'm in state S. So what is this picture first of all? Okay. There's going to be two levels of dots. One level of dots is going to be white dots. Those are states. Okay. The black dots are state comma actions. Okay. And and so white dots, black dots, white dots, black dots. Okay. Now what are we averaging? So let's focus on this equation. This is the same as before. Okay. We did not write the gamma times sum over p, but that's this expectation. Okay. This expectation of r is the first term. And expectation of the second term is the sum over p thing. Okay. So this exactly is what we're doing. So if you're in the state, there are two actions. Let's say. Okay. St is, let's say, little s a1, little s a2. Okay. Because little s a1, we can probably go to new state s prime 1, s prime 2. Let's say maybe there are only two possible states I can get to. Maybe here also there's only two possible states I can get to. So the recursive relation is just saying that for the optimal, here it's not the optimal, but in the q star of s comma a is related to these guys. Okay? The q stars at these four locations. Sorry, q star here. Sorry, q star here. Apologize. Q star of s comma a is related to q stars here. Okay, sorry, this averaging is for this thing, so it's a little bit confusing. But think of starting from this dot. Okay, I want to find q star of s comma a. You first go to the state because you're in s comma a, this randomly you get to some state. If someone randomly go to some other state, from there also there are probably like two actions. Okay, here there are two actions. At that place, whatever the q star of s comma a, that's being averaged. Okay, so this guy is related to this guy by averaging. So not averaging, sorry. The max of these two, and then average over what's the probability I'll get here, what's the probability I'll get here. That's the equation. Okay. Why the max of this? It's just a good question. What's the best way to explain? So why you're asking why there's a max here? I guess. Um, that I guess that's the definition of Bellman optimality equation. So, okay, I don't have a straight answer at the moment. Basically, Q star satisfies this Bellman optimality equation. Okay, it's very similar to Bellman expectation equation, but yeah, I don't have a better justification right now. Yeah.
Isn't that kind of like looking at a maze situation that we're just looking for the path that would have the maximal value, at least negative in that case, right?
Yeah. Oh, okay. So there's actually an intuition, which is the I don't know if you've seen dynamic programming. So basically, it's like saying, oh, what's the best value of me being in this state and taking this action? Is saying that, oh, the best value of being here is the same as uh, so. So have you seen this problem structure, substructure, or like what's it called? Um, Nesting of problems. So me being in the me getting the highest value here is the same as me taking so so this is this q star of s comma a here. So given this, what's the best thing I do? I'll take the max over a here, right? To do the best thing. That's what I should. If I do that max, I'll get the best action here, and I'll reach a state. I'll reach potentially many states from which I should also be doing the best action. So there's a recursive definition going on here. It's basically saying, oh, what's the best thing you can do from S prime onwards, and then one step backwards, what's the best thing I need to do now? Okay, so that's the problem substructure is a part of, I guess, dynamic programming literature is what's giving you the max here. Max is basically what's the best thing you can do at any given position is local best thing plus whatever you reach the best thing from that point onwards. Okay, so they have to be related to each other in this way.
Is the only reason, I noticed the only equation we have in policy is the optimal policy at the end of this. Is
Where in this equation? Or?
in this section of the, yeah, this one.
Yeah. Yeah. Okay. This section, I paused there is because. Yeah, so here so far we have not talked about how do I even have access to this guy, which is the transition probability function or the reward function, right? These two. Sorry. Yeah. So maybe cleaner picture. Yeah, I'm just saying that this guy and this guy, I have not even discussed how do we have handle on that, in the sense of that's the part we will need to learn, and that's the part we'll get there in 2 or 3 minutes. Okay. So far, if those guys are given, there's a recursive relation between state action value function. There's no issue here. The issue with the max operation was this problem substructure. Okay, so that's why it's called the Bellman. So this person figured this out in 1950s. Okay, so this is a nice substructure that the best cost to go plus the local cost is going to be the best cost to go now. Okay, so cost to go in the future and best cost to go in the future and the current cost to go future are related in this way. Cost to go, I'm only saying cost to go because it's like expected total return, right? It's like that's why I'm calling it cost to go. I guess reward to go maybe. Any questions? Or is it confusing? Okay, so we only have 10 minutes, so let's see. Okay, so what are we doing in the last part? In the last part, we are saying, okay, we don't even know that R function and P function, script P functions. So how are we gonna actually figure out the best policy? Okay, or collect this total reward? Because if you know this R and P function, I know exactly what the best policy is. If I can solve that max operation, which we did not go into detail, that max of pi or b pi of s, for example, I could solve that. Okay, that's a completely offline problem. But here I have to do trial and error. I have to, in different situations, do some exploitation. Okay, that's how I'll get an idea of how good the how good taking different actions in different states is, and therefore I'll figure out what's the best policy. Okay. And to be able to do that, basically we'll at least mentally think about it as doing two things. One is prediction, that is in a given, if I know, let's say I start with, like, think of jumping from a policy to a policy, which is like every policy is a mapping from state to actions. But okay, if I have a current policy, can you tell me how good that policy is? Okay, that's this prediction problem. In the sense, can you compute q pi of s comma a? Okay, so that will tell me a quality of how good the policy is. Okay, for every s comma a, if I can find this. But also I want to make improvement. Maybe I'm at pi, I want to go to pi prime. Okay, so that's if I can assess a value or quality of a policy, I can probably, that's one thing I need to do. And also going from a policy to another policy, an improved policy, is also another thing I need to do. So those are two tasks. They are called prediction and control tasks. And we'll actually jump over several steps and directly jump to Q learning, which does both prediction and control simultaneously. Okay, which is that it kind of estimates a local, it estimates q pi of s comma a, as well as makes a control as an improvement of the policy in every step of its algorithm, every time step. Okay, so we'll see that. So I will not get to Q learning today. Okay, I'll only get to what is called a Q value iteration. I mean, let's go stepwise. I mean, Q value iteration, again, I'm going to assume that I know script P and script R. And I'll show you how to do an iterative algorithm to solve for the best Q star s comma I. So what is the goal now for at least the next 5 minutes, 4 minutes, is just to understand how do I get Q star of s comma I. Okay, we saw the Bellman optimality equation, but how do I, there's an equation telling you, how, a property that the best guy satisfies the equation. But how do I find the best Q star of s comma I is the question. Okay, I can try to solve, that's a system of nonlinear equations because there's a max operation going on. But I can find the Q star of s comma a iteratively. Okay, that's what I'm going to spend the next 4 minutes on, and then we'll talk about Q learning at the beginning of next lecture. Okay. So yeah, so let's, I think, do I have this page? Yeah. So I think I'm jumping between two different things, but let's look at the first equation. V of st is related to the immediate reward plus v of st plus 1, right? This equation is fine, right? So that is pictorially represented here, where you are at st, that's related to these other uh, v. So the v here is related to the v's at these points. That's all this picture means, okay? And this expectation means average over from this state, I may get to s prime, s prime, s prime, s prime, all these different s primes. Average out all the v's here. That's what this expectation of these guys happening, and then the immediate reward that you get. Okay, so from here, if I take action a1, so because pi will tell me what action to take with whatever probability, and because of that, I'll get a local reward little r, and that's the averaging going on in pictorial sense. Okay, this is like a tree of all possible futures that can happen. Okay, so you might have seen this type of binomial tree if you did like options and futures or something like that. But anyway, all I'm saying is from this state, these are the only next states I can get to if I take different interactions, average all that out, and that's the recursive relation. And similarly, you have the similar relation for, I guess this was not, this is for a the Bellman optimality equation. Okay. Now, what I've changed is one thing, which is this arrow here. Okay, which means that I'm going to make this a recursive operation. I'll start with some initial q values, update to new q values, and again use those q values, apply some, keep doing an iterative update, and I'll tell you what the update is. Yeah. Yeah, so we're going to just do this step, okay? Turn Bellman optimality equation into an iterative update just to find, eventually after some iterations, find q star of s comma n. Okay? So we already know this equation, which was q star, this is the Bellman optimality equation, where I have highlighted the equality in the blue square, by which I mean I'm going to change that equality to an iteration, okay? Where left-hand side is updated based on right-hand side numbers, okay? So there's going to be iteration like k and k plus 1, for example, here, okay? So I'll start with some random numbers here, okay? If I have this, so now I'm in the situation where I'm not doing reinforcement learning. I know the models, then I can always do this left-hand side computation, right? Because I know script p and I know script r. I start with some random numbers. I'll get some new numbers, okay? Those new numbers are going to be this at every state action pair, okay? Now again, plug them back in here, and again apply this script r and script p. Again, get some new numbers, okay? And if you just do that, you actually get q star of s comma n. Okay, so that's a so why do we get that is actually some properties about this operation going on. Iterative operation, basically going from some previous value to new value, right? Some iterative update. So this operation happens to be a nice operation in the sense it's a contraction, is what they call it in that literature. But all it means is that this operation, this is a fact or a theorem saying that if you do this, start from any value, keep applying this operation again and again and again, you'll get to q star. Okay. So if you know script r and script p, okay. Yeah, and so I'll stop there because actually the slides are about q learning. So if you know the model, this is just offline problem. Okay, figuring out the best q star, and therefore if you know the best q star, finding the best policy is an offline problem. Now we actually don't know the model, so we have to do something which is trial and error. Okay, so that's where q learning comes in. So far this is just what is called q value iteration. Okay, so q learning is what I'll talk about next class. I kind of got too delayed this time. So that's it, I guess, for today. And if you have questions, just come forward. Yeah. So when you go to q learning, you wouldn't know these two. So what will happen is, as shown here, instead of doing the full average, we'll only do one sample, like try something and only update based on that sample, something like that. Yeah. So think of this q value iteration that we saw is somehow averaging the whole thing, or in this case, just the value iteration. It's called value iteration. Is just averaging the whole thing because you can go to all of the states in the future. Okay. okay? Because you have the P and the R function. But in Q-learning, you don't have the P and R function. You only sample one route, one step forward, and then do an update. Okay. So we'll see that pretty soon. I mean, I guess next lecture.